Welcome to Bill Sky the Assembly Guy, and this is going to be an extra video to help clarify some misconceptions or misunderstandings of what signed integers look like in the CPU. Now, I've had a number of students, I've had a number of people that have viewed my 2's complement video that are still a little bit confused or still don't understand fully signed and unsigned numbers. So that's why we're here. Let's go through this real quickly, just a few screens, and then we're going to do a demo. Now, if you notice on the title here, it says it's the programmer's responsibility. That's absolutely true. You as a programmer have to keep track of what variables, what CPU registers are signed or unsigned, and we're going to see some evidence of that. So, as a reminder, in a previous video, negative numbers in the CPU are stored in what we call 2's complement format. Positive numbers are not. And if you remember, 2's complement format was that you take all of the bits, you flip them, and then you add 1. And if you have a negative 1, you take the number 1 in binary, which would be all zeros with a 1, you flip all the bits, which would be all 1s and then a 0 at the end, then you add 1, and that is the representation of negative 1 in the CPU. Here's an example of what can be kind of confusing here. So we have the positive number 1, and that is stored as 000000001. That's a byte, 7 zeros and a 1. The most significant bit, as you can see here, is a 0, so that should tell you that that is a positive 1. You will never have a negative number with the most significant bit, a 0. So that will always be a positive 1. However, the confusion is, in my 2's complement discussion, I think I said that the most significant bit needs to be turned on, a 1, as can be seen in the third bullet here, to make that number a negative. Well, that's true, but you just don't turn it on. And in fact, if we do that, if we just turn on that 1 in the most significant bit, if you look over there in the little box, 2's complement procedure, you can see that 1601 converted into 2's complement is actually a negative 127. So unsigned, it's a positive 129 because the most significant bit doesn't have to be a 0 for it to be positive. It's how you take it. It's how you as the programmer decide that memory or that register should be treated. So if it's not a signed number, you're not going to use that most significant bit as a signed bit. It's going to be used as a value bit. So in the case of 1601, as a non-signed or just positive number, it's going to be 129. However, if you use that most significant bit as a signed bit, then the value is actually going to be a negative 127, taking 127 and converting it into 2's complement. So here's an example program that we're going to look at in the demonstration, and that's coming up next. And let's just do it. So I've got my Linux up and running. Now you can do this on Windows. You can even do this on ARM. The statements will be a little bit different on ARM, but you can even do this on ARM. So here's our little program, and let's go through what each one of these lines does. Well, I have a reserved byte up here in the BSS section, and that's called saved byte. It's a single byte, RESB, reserved byte. I want to reserve 1 byte. Then in my code, I move 1 with 7 zeros ahead of it. I don't have to put those zeros there, but that's a binary move because of the B at the end. I move 0000001 into AL, and then I move AL into the saved byte variable or reserved memory area with this statement. Now the reason why I'm putting it in the memory area is because the debugger lets us look at the memory areas in many different formats. We can look at it as signed or unsigned. Where the registers you can't. So then what I do is I take that number 10000001, and that's 1 with the most significant bit turned on. And some people think, well, now that's a negative 1. No, I'm going to prove to you it's not. We now move that to AL, and then we move that into the saved byte memory area. And with that, what I'm going to do is I'm going to debug it, and I'm going to show you exactly what the values look like in memory. So we built it. It looks good. I'll bring up the terminal. And let's go ahead and start the debugging. So I'm going to move just a 1 into AL, and you can see the register right there shows a 1. Now I'm going to move AL into that saved byte variable. Now before I do that, I'm going to go into memory, and probably what you're going to have is something that looks like this. You're going to have hexadecimal values. So I'm going to go into the memory, and I'm going to say ampersand saved byte. It was already there, but I'm showing you how to do it. And we can see that saved byte right now is a 0 because it's uninitialized. We're kind of lucky it's a 0. On Windows, it might be garbage. So now we're going to move AL, which is 1. We're going to move that to saved byte. And there's the 1. Now let's right-click on this and say signed decimal. And you can see as a signed decimal number, it's the number 1. Why? Because the most significant bit up here was not set. If I right-click on this and I say unsigned decimal, it's a 1 because we use that most significant bit as part of the value, but that didn't give us any additional value because it was a 0. Now let's do the next line of code. The next line of code is going to move that -1 because we just turned on the most significant bit, but we left everything else the same as just a 1. Let's see what happens. It's a 129. Now how are we viewing that? Let's view that as a unsigned decimal, and it's 129. And in the presentation, that's what I said. It's 129. Why? Because it's unsigned decimal. We're using every single bit to use as the value of the number. And if you do that math in a calculator or by hand, you'll see that's 129. Now let's right-click on that and say signed decimal. It's -127. Why? Because if we take the 1, 0, 0, 0, if we take this 1, 0, 0, 0, 0, 0, 0, 1, convert it to using 2's complement, it'll be 0, 1, 1, 1, 1, 1, 1, 1. We take the decimal value of that, which would be 127, and we just manually stick a minus in there. We're doing that for our observation of what it actually is a negative number. In the CPU, it's not that. But the CPU, if we as programmers mean it to be, it is a -127. So how is all this possible? It's because the CPU has no concept of signed or unsigned integers. It doesn't know what you mean it to be. The architecture of the CPU as such is that 2's complement is used as the primary communication or conversion method of negative and positive numbers, and it's something that you as the programmer have to keep in mind. And what do I mean by that? That means that each variable or integer value the programmer manipulates must be treated as either signed or unsigned by you, the programmer, and you have to keep track of this. The assembler will assist you in no way whatsoever. It will not give you any help. So some rules that I've used in my career: never mix signed and unsigned integers when doing comparisons. In fact, even in C and C++, the compilers, if you do that, as you can see by this code here, this code has 2 variables. It has a signed, a signed int, which is equal to 0, and then it has an unsigned int, which is equal to 0, and we have an if statement there. And the if statement is comparing the two. And the compiler even says, warning, you don't want to do this. It doesn't give you a compiler error. It will actually run, but it may give you results that are not what you think they are. So even C and C++ say not to do that. Since the assembler won't even give you a warning like that, it won't give you a warning. It's going to tell you nothing because the assembler is not as intelligent as a compiler. It doesn't really do anything with your code. It's assuming that you know what you're doing. So it's up to you to make sure you don't do this when comparison. Some more rules. It's also important that if you are going to use signed and unsigned numbers while multiplying or dividing, you do it carefully with the correct instructions. Adding and subtracting between signed and unsigned numbers will work, but you should always assume the result will be signed. And I kind of feel that way about multiplication and division too. Now that doesn't mean you have to do that. If you know that all of your numbers are going to be unsigned, they're all going to be positive numbers, then you don't really have to worry about that. You just have to check the overflow and the carry flags after your mathematical operation. And if you haven't gotten there yet in the videos, take a look. Yet some more rules. Name your memory labels in a way that will help you remember what memory will be signed and unsigned. So an example, a signed variable might have an S underscore in front of it, S underscore variable name. An unsigned might have U underscore variable name. You might decide that all numbers are unsigned without anything in front of the variable name. Only those that have an S underscore will be signed. So it's up to you. If you work at a company, you might want to find out, do they differentiate between signed and unsigned, and what kind of variable naming standards do they have? So in conclusion, it's really the programmer's responsibility to keep track of signed and unsigned integers. To be safe, you can assume everything is signed. However, you'll lose some positive range. Like for instance, a signed number, you go from a little bit smaller than 2 billion to a little bit bigger than 2 billion. Negative 2 billion to 2 billion. However, unsigned, you can go all the way up to 4.3 billion. So if you decide to make everything signed, if you're not going to be dealing with those huge kind of numbers or very, very tiny numbers, that might be a way to do it, is just to make absolutely sure you assume everything is signed. Use sign extension instead of zero extension. That would be the move SX as opposed to the move ZX. If you're not sure, move SX will always help and will always do it correctly. Even if the sign is 0, it'll do exactly the same thing. The sign bit, the most significant bit, even if that's 0, it'll do the same thing as move ZX. It'll move 0 up into all those upper bits. And again, the CPU and the assembler will be of no help here. Now, just to let you know, this applies to both x86, 64, which are the Intel AMD chips, CPUs, as well as ARM processors. You've got the same problem. Linux, Windows, Mac all have the same process, the same, I don't want to call it a limitation, but you might think it is, but it's just the way the CPU is built. We as programmers need to code around it. So I hope that's helped you out a little bit more to better understand signed and unsigned. And I believe it's kind of like riding a bike. You kind of have to practice it, do it slowly, just like on a bike, and look at the debugger, let the debugger lead the way. Hope to see you at our next video.